Hello! So today we're going to discuss the limit comparison test and the alternating series test, which are tests for convergence and divergence in series. So what is the limit comparison test? What does the limit comparison test say? Well, before we can apply the limit comparison test, there has to be one condition that is satisfied, and that is your series A sub n and series B sub n have to be series of positive terms. So you cannot apply this if you have terms that you subtract. Also, A sub n is typically refers to the given series, and your B sub n typically refers to a series that you chose for comparison. That's why it is also somewhat similar to the comparison test, but it's also different in what you do. If your limit of a sub n over b sub n as n approaches positive infinity is equal to L, where L is a positive real number, then either both series converge or both series diverge. It's always either one of these. So you either have two series that diverge or two series that converge. And this means that you can end up with an answer like pi, e, which are irrational numbers, or 17 over 3, a rational number, or 4, which is just a positive natural number. However, you cannot end up with something like negative 4, and that means that you have an inconclusive test result. The second part of the theorem says that if your limit of a sub n over b sub n as n approaches positive infinity is equal to 0, and your series of b sub n converges, the series you chose for comparison, then your series of a sub n also converges. So what if we end up with a positive infinity for the limit? Third part of the theorem says that if your limit of a sub n over b sub n as n approaches positive infinity is equal to positive infinity, and your b sub n is known to diverge, then your series of a sub n also diverges. Note that you need some skill in choosing the series b sub n for comparison. So you need to do some practice, and you have to be familiar with what kind of series you can choose to compare for this comparison test. Some tips in choosing b sub n: you have to find out if b sub n is convergent or divergent before you compare your a sub n to it. And you also have to choose a b sub n that's relatively simple compared to a sub n so that you can test it for convergence or divergence. So what about the alternating series test? So for the alternating series test, or AST, we consider a series negative 1 raised to n b sub n or negative 1 raised to n minus 1 b sub n, where b sub n is greater than 0 for all n. So what does this mean? The b sub n greater than 0 for all n simply means that this series would be a positive series if it weren't for this factor specifically. What does this part mean? The n minus 1. It simply means that in your original series, you managed to factor out a negative 1, perhaps in the denominator. So now you ended up with negative 1 raised to n minus 1. So what's the first part of the alternating series test? If the sequence b sub n, note that it says sequence here. If the sequence b sub n is ultimately decreasing and the limit of b sub n as n approaches positive infinity is equal to 0, then the series is convergent. Warning: if any of the two conditions is not satisfied, the alternating series test is inconclusive. So both of these conditions need to be satisfied. It's not like in the LCT where you have 3 cases. So both of these come hand in hand. And in the case that you end up with you end up satisfying only one of these conditions or none of them, you must use other tests to determine the convergence or divergence of your series. So for our first problem, we have to determine if the series below is absolutely convergent, conditionally convergent, or divergent. And we have to justify our answer. So right away, we can kind of tell that we can't apply the alternating series test because there's no factor of -1 raised to n here. So we can try using the limit comparison test to solve this problem. And we start the limit comparison test by choosing a series p sub n. And for this problem, we choose b is equal to 1 over n ln of n. So before we proceed with the limit comparison test, we first have to check if this series that we chose is divergent or convergent. So we can have a comparison. So one can verify that our series B diverges using the integral test as follows. So you might be wondering, why did we choose 2 as the lower bound for this integral? Well, that's because the result for this integral, you might not end up with an actual answer if we have 1 for the lower bound for this integral. And we can see that here. So we integrate this, integrate as usual. And the 1 becomes problematic in this part here. So we have ln, so we would have ln1, which is equal to 0, and then ln of 0, which is undefined. So you would have infinity minus undefined. That's why it's kind of problematic, and we just sliced off a little bit of the integral. So we replace the 1 with 2, and that's why it's roughly equal to. So verifying this limit, we can see that it's equal to positive infinity. So we can tell that this series is divergent. You notice that both series have positive terms. So now we can kind of apply the limit comparison test. So now we consider the limit of a sub n over b sub n. We would have n plus sine squared of n over n squared ln of n. You would see that this can cancel out the ln n and the n squared. So now we would end up with n plus sine squared n over n. And now if we further simplify this, you would have n over n plus sine squared n over n. Now n over n is just 1. And then notice that there's still a limit symbol for sine squared n over n. So since the sine function fluctuates anyway, and n is positive infinity, you would end up having 0. So this expression would end up being 1 plus 0, and 1 is a positive real number. So because of this, since the series B is divergent and the value of our limit is a positive real number, we can conclude that the given series is divergent by the limit comparison test. Yay! Okay, so for our second problem, you have to determine if the series below is absolutely convergent, conditionally convergent, or divergent. So right away, we can kind of tell that we can apply the AST because there's a factor of -1 raised to n. So we just proceed with the AST as usual. So we consider sequence a sub n and define our b sub n to be the absolute value of a sub n. or just our a sub n with the negative 1 raised to n factor removed. So these are the two conditions that we have to satisfy for the alternating series test. We claim that the sequence b sub n is decreasing for n is greater than or equal to 4, and the limit of b sub n as n approaches infinity is equal to 0. So now we suppose our n is greater than or equal to 4. Then we would have limit of b sub n plus 1 over b sub n as n approaches positive infinity. And we just substitute as usual. And in this part, we just multiply it by 1 over e raised to n plus 1 over 1 over e raised to n plus 1, so that we can evaluate this at infinity. So now we would end up with this expression. And since this is just sine n over e raised to infinity, we would have 1 over e, and this just cancels out. And this also just cancels out because it's just similar to this term here. So we would have 1 over e over 1 plus 0. So that's just 1 over e. And then if we evaluate this, we would have n over n times 1 plus 1 over n. So that's just 1. That's 1 cubed times 1 over e. So now we have 1 over e. Since the limit of n plus 1 over n as n approaches infinity is equal to 1, nagka-typo lang, and these approach 0 as n approaches positive infinity. So, since the limit of this expression is 1 over e, which is less than 1, the sequence is eventually decreasing by the definition of a limit. Moreover, the limit of our b sub n as n approaches infinity is equal to this. So now this looks kind of intimidating to evaluate at infinity, since we can't factor out n cubed, and this is just an indeterminate form of infinity over infinity. So we can apply L'Hopital's rule. We just differentiate the numerator and the denominator, and then, oh snap, it's still scary to evaluate at infinity. So now we just apply L'Hopital's rule again. And then, oh snap, it's still scary to evaluate at infinity. So now we just apply L'Hopital's rule again. So now this looks kind of easier to evaluate because you just have a constant as your numerator. So you just have 6 over e raised to infinity minus cosine of infinity. So you would just have 6 over infinity minus something between negative 1 and 1. So that's just 0. Since it's just 6 over infinity, para mawawala lang si cosine n. Thus, by the alternating series test, the given series is absolutely convergent. It's also good to note here that the ratio test can be applicable in testing the series of b sub n.